Log on, tune in, find out. Another good idea from Cambridge.
We have Jeff Harvey from University of Chicago, who will be talking to us about Moonshine and mock modular forms.
Right. Okay, so I want to talk about a kind of structure and there are at least 4 components to the kind of structures that I want to talk about. So you have modular objects. You have groups, finite groups, often sporadic groups. String theory. And then some kind of often large, interesting algebra. And we have roughly 2 classes of whatever you want to call these things that exhibit all 4 of these features. One of them is monstrous moonshine, which has been developed really over the last, I don't know, say 40 years, something like that. And in monstrous moonshine, the modular object is the modular function j of tau. The group is labeled in different ways, but it is the monster group, and it's the largest sporadic group. So finite groups fall into infinite families, and then 26 finite groups that don't fall into any of the families, and the monster is the largest of those 26. The string theory interpretation of this involves the bosonic string, or you can also do it for the heterotic string, compactified down to 2 dimensions. And I will say more about this on a Z2 asymmetric orbifold. And the algebra that appears here in the mathematical literature is known as a vertex operator algebra, and it was axiomatized, defined by Borchards, but it's recognizable, after a little effort, to a string theorist as the algebra of chiral vertex operators in the conformal field theory defined by the bosonic string on this 24-dimensional torus modded out by Z2, defined by the operator product expansion of those chiral vertex operators. And starting about a year and a half ago now, so there are other, I mean, this is the most famous example. There are some modifications of this kind of construction that lead to a few other analogs, but they all have roughly these same kind of ingredients. And there now seems to be a second main class of examples of this, where, which I guess sometimes called the K3M24 connection, or sometimes referred to as Matthew Moonshine. And in this example, the modular object is something that I will call H21 of tau, and the notation will become clearer later on, and I'll explain what this is. It turns out that this is a mock modular form. The group is the largest Mathieu group, and the Mathieu groups were, I think, the first of the sporadic groups that were discovered. The string theory involves type 2 superstring theory on K3, or perhaps on K3 times T2. And the algebra, I would say, is not completely understood or completely clear yet, but it probably has something to do with something called a generalized Kac-Moody algebra, which is related to an object called phi 10, which is a Siegel form that enters into the counting of quarter BPS states in N equals 4 string theory. And I think, or it may be related to the BPS algebra of the BPS states in string theory on K3. So I think this is a very interesting development for at least two different reasons. One is it's just intrinsically mathematically very interesting to have connections between such different things. This connection between the monster and J of tau was an enormous surprise when it was first discovered, and perhaps still not completely understood. So to have a connection between some other group, sporadic group, and some other kind of modular object is very interesting. And at least so far, it's not understood in the same kind of detail as understood over here.
Who understood this?
So the original paper is due to Oguchi. I'm going to say more about all of this. This is just kind of an outline. But Oguchi, Oguri, and Tachikawa, and I forget the date, but there's a paper on the archive which you can find. So the other reason I think it's interesting is, aside from the mathematical interest, it's very curious that bosonic string theory enters into this construction. And if you have any hope that these kinds of exotic and very special structures are connected to the real world, and the string theory is connected to the real world, then it's certainly very interesting to have something like that going on in a supersymmetric string theory involving a compactification that preserves space-time symmetry down to 4 or 6 dimensions. It's not the real world, but it's infinitely closer to the real world than going down to 2 dimensions in the bosonic string. So I think it's a very interesting development. And so I've been asked to give 2 talks that are more pedagogical than usual. So I'm going to try to develop some of this a little more slowly than I would otherwise. And towards the end, I will talk a little bit, but without full details, about some work that I've done with Miranda Chang and John Duncan. And this K3M24 story involves sort of the starting point is the elliptic genus of K3 surfaces. And that pair of the elliptic genus of K3 and M24 is one of 6 examples where you have an object phi L and a group GL. This is going to turn out to be a weight 0 and index L minus 1 weak Jacobi form. And this will be a finite group. And L takes values in the set 2, 3, 4, 5, 7, and 9. And in our lighter moments, we sometimes like to refer to this and the second example as Icasa chi tetralogy. This follows a nomenclature for labeling n-gons for large N invented by John Conway. So Icasa chi tetra means 20 plus 4, and ology is the study of, essentially the study of 20 plus 4. And this is supposed to remind you of the 24 in the Matthew group, and it's also supposed to remind you of the 20, 4 even self-dual lattice that enters into the cohomology of K3 surfaces. But it's too hard to remember how to spell this or pronounce it, so I doubt we'll use that in the title, but it's kind of a nice word to keep in mind. Okay, so, yeah.
It's a simple thing. Here, this thing where you write all heterotic.
Yes.
I mean, in some sense, isn't type 2 on K3 the same as the heterotic string on T4 or whatever, which one is, yeah, T4.
Yeah, so I suppose, yeah, so you could say over here I could do heterotic on T4, but the equivalence is non-perturbative, whereas the more detailed understanding of what's going on here at present involves the elliptic genus of K3, which just counts perturbative BPS states. And in the heterotic theory, those would be mapped to non-perturbative states. Now, I think probably in the grand scheme of things, you ought to be looking at both perturbative and non-perturbative. But the full action of M24 is not really understood, even on the perturbative state. So, yeah, it's. Okay, so here is an outline of what I will try to cover. So the first thing is some introduction, which luckily we're done with. Just so that we're really starting from a point that everybody knows, I will remind you about a few basic facts of modular forms and how they enter into string theory. Without going into full details, but hopefully enough to make it a little more understandable, I will talk about some of the constructions in monstrous moonshine, kind of from a stringy point of view. I will discuss this K3M24 correspondence, what it involves. One of the things that it involves are Jacobi forms, and I will tell you some facts about Jacobi forms, and in doing that, I will talk a little bit about one of our generalizations, the m equals 3 example. Then I will try to explain a little bit about what Mach modular forms are, and a particular kind of Mach modular form, which are Mach theta functions, which originated in a letter, the last letter that Ramanujan wrote to Harvey in 1920. I'll say a little bit about what are called Thompson series, or Mackay-Thompson series. And if I have time at the end, I will tell you a little bit. Yikes, that doesn't go up. It comes out though? Is that better? What do you know? I'll tell you a little bit about the properties of the groups GL. Does this one also come out?
It does.
Brilliant. Well, that's nice. All right, so that's the plan of the lectures, and please ask questions.
Is there a similar story when you consider some Calabi threefold instead of K3 times threefold?
The elliptic, it depends upon what the generalization is supposed to be, but the elliptic genus of a Calabi threefold is unique. There's just, it doesn't depend on anything, really. And as far as I know, there's no evidence of moonshine for it, but it's possible that there is some. Well, it'll turn out that in looking at this generalization, the connection to the elliptic genus will somewhat be lost. And so I'm not quite sure what that means. But I think, in trying to understand what's going on in this story, if you can't make direct progress, sometimes it's useful to enlarge the structure or class of objects you're looking at, because once you enlarge it, you recognize that it fits into some other category of things that you might not have realized. So I think by enlarging this, we hopefully eventually that will help to shed some light on what's really going on. Okay, so let me just say a few things about modular forms. I think this is probably all familiar, so I'll be fairly brief. So I consider tau as an element of the upper half plane. I'll usually write Q for e to the 2 pi I tau. And there is a natural action of SL2Z given by tau goes to A tau plus B over C tau plus D. And a modular form of weight k is a holomorphic function from the upper half plane to the complex numbers, which obeys f of, I'll call this gamma of tau. F of gamma of tau is equal to C tau plus D to the k times f of tau. Now, f of tau is equal to f of tau plus 1. So you can write f as a Q expansion. And then you classify forms as either cusp forms, just plain old modular form of weight k, or a weak modular form, depending on certain conditions on the coefficients, which are also linked to the growth of the coefficients. So the coefficients should be 0 for n 0 or negative for a cusp form, and the coefficients then grow as n to the k over 2. A modular form has an equals 0 if n is strictly less than 0. And those also have polynomial growth, but twice as fast as cusp forms. And weak modular forms have an equals 0 only for sufficiently, there's some finite but negative number below which they vanish.
So what's k?
K is the weight of the modular form. So k is the same k as over here. And these have exponential growth for some constant c. So it's a classical result, which I certainly won't try to prove, that the space of weight k modular forms is generated by the Eisenstein series E4 and E6, where E k of tau is defined by summing over all integers C and D that are relatively prime, 1 over C tau plus D to the K. So this transformation law for modular form shows that you can kind of think of this as taking the function 1 and then summing over all its images under the action of the modular group. And if you take something and sum it over a set of group actions, at least if that converges, you either typically get 0 or you get something that has nice transformation properties. And that's what happens here. You get something that has nice transformation properties.
Shouldn't the sum be over positive or anyway non-zero? But I thought there was something about them being. I guess C and D cannot both be 0, obviously.
Right. I think they have to be relatively prime, and
okay, that's sufficient.
I think that's sufficient.
Do you have to worry about the convergence properties in any of these? Or
Yes, you do have to worry about the convergence properties, and this sum converges for K. I mean, so you could try, so there is a convergence issue. If you look at K equals 2, then it turns out that this sum does not converge absolutely, but you can kind of order it in a way to make it convergent. But when you do that, you lose the good modular properties. And so there is something called E2, which I might mention later, but E2 of tau doesn't transform as a modular form of weight 2, but E2 hat, which is E2 of tau minus, I forget, something like 3 over pi times the imaginary part of tau, I'm not sure about that coefficient, does transform well, but it's not holomorphic. And actually, that's a nice question, because it turns out that this is the world's most baby example of a mock modular form. So a mock modular form is something where the holomorphic guy doesn't transform well under modular transformations, but you can add something to it to make it transform well, but the thing you add is not holomorphic.
Can I just ask about that weak modular forms?
Yeah.
Does that say n? So it's just a thing. Does that say n much less than 0?
Yeah, I think that's just a notation that says that there's some finite but negative n, and the coefficients vanish for any n below that
I see.
value. All right, so if you look, for example, at the Q expansion of E4, it's 1 plus 240Q plus 2160Q squared plus dot, dot, dot. And I want to give a few examples of how things like this arise in string theory, even though we all sort of know them. So in string theory, for example, in the heterotic string, we encounter E8, and we encounter the theta function associated to E8, which is a sum over vectors in gamma 8, the E8 root lattice, q to the p squared over 2. And you use the fact that gamma 8 is even and self-dual plus Poisson resummation to show that theta E8 is a weight for modular form. And one of the sort of amazing and powerful things about modular forms is that the space of them is generated by E4 and E6, so the ring is generated by E4 and E6, so you can multiply them and you still get a modular form. You can take sums. And you can classify what things there are at a fixed weight. And this tells you that there's only one guy at weight 4, so without even having to compute anything, if you buy this theorem, you know that the E8 theta function is the same as E4 of the Eisenstein series, just because once you've shown this guy has a weight 4 modular form by doing a calculation, there's a unique weight 4 modular form, and so they have to be equal. And so you get all sorts of amazing identities just from the fact that there are a finite number of modular forms of any given weight. If you want to make a cusp form, so to make a cusp form, you're not allowed to have...
Can I just ask a trivial question
Yeah.
about notation? So MK is the space of modular forms?
MK is the space of modular forms of weight K.
But you also might denote an individual one as MK.
No, I don't think so. So here, this... I guess what I should say is the space of all modular forms is generated by E4 and E6, and if I want to look at weight K, then I have to look at all products so that the total weight is K. I'm sorry, I'm being a little sloppy.
I just wanted to add that.
Yeah. So to make a cusp form, you're not allowed to have a constant term. You're not allowed to have q to the 0, but you can construct such a thing. If you have E4 and E6, then the first thing you can make, where some power of E4 and a power of E6 have the same weight, is weight 12, where you can take E6 squared or E4 cubed, and if you subtract them, that will clearly cancel off the constant term, and then it's conventional to divide by 1728. Call this thing delta, and this is also familiar in string theory because it's the 24th power of the Dedekind eta function, and of course 1 over eta to the 24th shows up in the partition function of the bosonic string. So it's also something that we are kind of familiar with. Now,
So Jeff, in your notation, eta itself is not a modular form then, right?
no, eta itself is not a modular form.
That's because it doesn't, it's not invariant under tau plus.
It doesn't transform like this. So eta, well, first of all, it would have weight a half.
Right.
But the other thing is, in its modular transformation property, it has a 24th root of unity. It has a phase. So, of course, you do want to include such things, but strictly speaking, it's not a modular form. What it is it's a modular form with a multiplier system, some one-dimensional representation of SL2Z. And you can either take the 24th power to get something that's a true modular form, or you could ask whether it's a modular form not for the full modular group, but for some finite index subgroup. So, yeah, but strictly speaking, according to the standard definition of modular forms for SL2Z, eta is not a modular form. So this is a distinction that physicists often kind of gloss over, because if there's some phase in the transformation law, it doesn't really bother you. You just keep track of it and go on your way. But if you want to be a little more precise, then you, yeah. All right, so at weight 0, the only modular form, which we really would call a modular function, there's no, there's no c tau plus d to the k in the transformation law. We just have f of gamma of tau is f of tau. The only modular function is a constant, because this function is defined on the upper half plane, modded out by the action of SL2Z, and that fundamental domain has genus 0. So it's like trying to define a holomorphic function on the sphere, and you can't do it except for a constant. But if you allow sort of a pole at infinity, that is, tau goes to I infinity, then you can have such things. And the modular function that you get of weight 0, you can construct in a variety of ways, but one is to take E4 cubed, which has weight 12, and divide it by delta, which has weight 12. So this gives you something of weight 0. But it has a Q inverse in its expansion, so that shows you that it has a pole as you go off to infinity, go to Q equals 0. There's then a constant here. And in general, if you allow things that have poles, then you can consider any rational function of j of tau, and that's a fairly standard thing to do. So j of tau is the generator of the field of functions that are SL2Z invariant and have simple poles. Now, this also arises in string theory. So let's consider the bosonic string compactified down to 2 dimensions on a 24-dimensional torus. And we will choose the torus to be one that I get by taking the quotient of R24 by an even self-dual lattice. And there are, I think, 24 of those called Niemeyer lattices, plus the Leach lattice. And if you do that, then the partition function of the bosonic string is easy enough to compute. It's going to be the theta function of this lattice divided by eta to the 24th, all squared. So the reason I did this is so that the partition function will just holomorphically factorize into 2 products rather than a... So it's a rational conformal field theory with just one block. And that is j of tau plus a constant squared, where the constant depends on the lattice. And what does the constant term correspond to? Well, in string theory, we get terms that would, where, I get this term. These are massless fields in space-time by either taking an oscillator acting on the vacuum or a state with p squared equals 2. So the constant depends on how many states you get here. And if you want to have as few as possible, you can get rid of all these states by taking this lattice to be the Leach lattice, which is the unique even self-dual 24-dimensional lattice that doesn't have any points of length squared 2. So there is now a famous observation due to John Mackay that 196884 is 196883 plus 1. And if I were really good, I would have memorized the next 7 terms, but I haven't. But here's the next one. So 2149360 is equal to 2129686 plus 196883 plus 1. And this number and this number are dimensions of irreducible representations of the monster. And the monstrous Moonshine story kind of, I forget exactly when the paper came out. I think, I don't know, 68, 70, something like that. There was a paper by Conway and Norton who took this observation. This observation suggests the following. It suggests that there is some infinite set of vector spaces, VM, and that J of tau has coefficients which are the dimensions of these vector spaces, and that the monster acts on the VM and hence on V. So in other words, that this is a module for the monster. So Conway and Norton took this idea, and I think at the time the monster group was not actually known to exist, but if it did exist, its character table was known. And there was no construction of any conformal field theory that had the monster acting on it, but nonetheless they computed all sorts of interesting things, including, well, some Thompson series, which I will explain later, and found all sorts of remarkable facts. But I don't want to really go into the details of that yet. So instead, let me say a little bit about what Frinkel, Lepowski, and Merman did. So suppose that you were faced with these facts and you wanted to try to construct some conformal field theory that had the monster acting on it. And you knew that the bosonic string gave you J of tau plus a constant as its left-moving partition function. And you knew that there was this observation about these numbers. Now, the one immediate problem you would face is that the constant term here is not going to correspond to a representation of the monster except for some number of copies of the identity representation. For example, if you take the Leach lattice, then that constant is equal to 24. There are 24 massless states, these U1 to the 24th gauge bosons. So you would have to get rid of those states somehow. Another way of saying this is that in string theory, on T24, it's the bosonic string, we have moduli, and the vertex operators are just di dxj. Those are all dimension 1 guys. And if I if I perturb the theory by adding these, I just move around in the Noreen moduli space. So if I want a theory that has some special symmetry like the monster, I can't possibly be allowed to move around in moduli space and still have the monster act everywhere. So I need to get rid of the constant term. I need to kill the moduli. So that's something we want to do in string theory. How do I do that? I simply take the left-moving bosons and I perform an orbifold, a Z2 orbifold. So I take the xi's and I take them to minus xi. Now, that preserves modular invariance, although it's not completely obvious, but it preserves modular variance basically because the twist field for this orbifold has dimension 3/2, and it therefore satisfies level matching. There are physical states in the twisted sector. It kills these moduli, and if you twist by this, you get a theory whose partition function, so the orbifold partition function, is going to be J of tau with no constant term squared, because it can't be anything else. You've gotten rid of all the massless fields. It preserves modular invariance. It holomorphically factorizes, and that's the only thing you can get. So this asymmetric orbital fold is a candidate because you fixed all the moduli. You can't vary it anymore. And it has a partition function that has an exact correspondence between its coefficients and the dimension of representations of the monster.
Just a little confused here. So j of tau has its own constant term, right? Just as a function.
Yeah.
And you haven't written what it is. That's a fixed number.
Okay. So yeah. All right, so what I really meant here is that if I take the Leach lattice, then what I get here is Q inverse plus 24 plus 196,884 Q plus dot, dot, dot. You're right, J of tau has its own constant term. I mean, the thing is, I can change the constant term without changing the modular property, because
Right.
so.
But so here when you say j of tau with no constant, you mean j of tau
I mean Q inverse plus 196,884 Q plus dot, dot, dot. No constant.
So it's
term.
really j minus that constant.
It's J minus that constant. Yeah, it's J, I don't know. So I think some definitions have the constant equal to 744, and so it's J minus 744. I think the definition I gave has 744 because that's 3 times 248, I think. No, that can't be right. No, yeah, it is right. Okay, I think it's right.
Similarly with that Norton and Conway decomposition, what was the relation between the VMs, the VM modules, and the dimensions of the monster, the irreps of the monster?
So the dimensions of these vectors, so this is just a conjecture so far, I mean at this level. If you see a set of numbers there that you can write as, in a non-trivial way, as sums of dimensions, one natural explanation for that would be that those numbers are the dimension of some vector space which carries a representation of the monster.
Or several?
Well, it might be a reducible representation, and it has to be a reducible representation because the monster has only a finite number of irreducible representations, and these coefficients grow without bound. So eventually, you have to have a sum of representations. So whatever that sum is, there's some in general reducible representation of the monster that it conjecturally corresponds to, and so you interpret that as being the dimensions of some vector space. But Conway and Norton didn't know what these vector spaces were. But it didn't matter. They could still do computations. I mean, I'm a little bit out of the order I was going to say things, but let me explain what I mean by that. So the dimension of VM, you don't know what it is, but let's just assume there is such a vector space. So the dimension of VM, I now imagine that somehow the monster acts on this. Well, the monster has an identity element, and the dimension is just, sorry, not the dimension, it's the trace of the identity element acting in the vector space VM. Because, right, that's just a unit matrix of size, the dimension of VM. Well now, if I think that I have some action of elements in the monster, I can replace this by the trace of G acting on that vector space. Well, I don't know that either, really, because I don't know the vector space. But if I know how this decomposes, I can compute this from the character table. And furthermore, it's an invariant under conjugation of G, so it depends only on the conjugacy class. So there's a function, which you might call, well, Tg of tau, which is the trace of G acting on Vm, Q to the m. And without knowing what the vector spaces are, but just having a conjectured decomposition, you can compute these from the character table. And there are 194 such functions. And one of the things that Conway and Norton found, which I'll mention later, is that these had very special properties, these 194 functions that you found.
Is there a way to decompose the higher power Q, pushing the higher power Q?
Is there a way to decompose them?
Unique method of decomposing higher power Q.
Well, to deduce what that decomposition is, you either, as far as I understand it, you have to do one of two things. If you don't know what these spaces, I mean, one thing is to actually find a construction of these VMs. That's what Frankel, Lepowski, and Merman eventually did. And then it's just a concrete computation. If you don't know that, so you're Conway and Norton, then it's kind of like a giant Sudoku puzzle. As you go further and further out, you have more and more possibilities for how you could decompose this number. But given a decomposition, that implies a particular set of terms in the Q expansions of these other 194 functions. If you think that these things have special properties, which they found that they did, then the coefficients in their Q expansion are not arbitrary, but they have to match with that special property that you found. And so then you get constraints on what the decomposition could be by matching onto the modular properties of these functions. And so that's what they did.
Presumably such constraints rule out trivial possibilities like just one of the...
Like 196, 84,
ones.
yes, right. Exactly. Yes?
The relationship between the monster and the chain variant is only based on numerical evidence? I don't understand if the evidence are only numerical.
No,
There
it's...
are more
No, I'm
mathematical evidence also.
no, so, I mean, maybe I should explain a little bit about the history. So initially it was based on numerical evidence. That was the content of this paper by Conway and Norton called Monstrous Moonshine. Then, I believe around the mid-1980s, there was a construction by Frankel, Lepowski, and Merman of, I mean, they didn't say it in this language because they were not using the language of orbifolds and conformal field theory exactly, but there was a construction of this holomorphic conformal field theory. And in that holomorphic conformal field theory, you can prove that the monster is the automorphism group of that conformal field theory. So that took it from the stage of conjecture to a rigorous mathematical construction where you could prove things. And I'll say a few things about what's involved in proving that. Then the next stage was to prove certain properties of these Thomson series, and that was done by Borchards in, I think, the early 90s, mid-90s, and resulted in the Fields Medal in 1998. So now, I think most of the main conjectures have been proved rigorously in that you can prove that the monster is the automorphism group of a conformal field theory that tells you exactly what these vector spaces are. And you can prove the conjectured properties of these Thomson series in a way which I'll say a little bit about, but won't give the full details. But I guess I'm partly telling the story in this historical way because in this K3M24 thing that I want to talk about at some point, I think we're at a stage which is sort of like after Conway and Norton, but before the Frankel, Lepowski, Merman construction of the CFT. That is, we have a lot of numerological evidence that there's a connection between K3 and M24, but we haven't found an explicit construction that tells us exactly how M24 acts on some set of vector spaces, and that's what we would like, that's one of the things we would like to find. So the second part of my story is conjectural now, but this first part is just reviewing things that are now proved. Okay, so I may be spending too much time on Monstrous Moonshine, but I don't know. Am I?
No.
No? Okay. And if I am, what can I do about it? All right, so I'm certainly not, don't have the time or the ability to prove that the monster is a symmetry of this conformal field theory, but I can mention a few things which might be helpful in understanding how that was done. And if you ask me any questions, I probably will not be able to answer them. But so one of the things that went into proving that was the fact that the monster has two special involutions, that is, elements of order 2, which I will call I and sigma. And so I'm not going to, we'll just have to take it on faith as something that was shown by people that know a lot of finite group theory, that the monster is generated by the centralizer of I and the involution sigma. So the centralizer of I is the set of elements of the monster such that G inverse is equal to I. So they commute with this involution. So in this conformal field theory, you can identify, modulo a few subtleties, what these guys are. So in any, certainly in a Z2 orbifold, there is always a quantum Z2 symmetry. I mean, it's often called a quantum Z2. There's nothing particularly quantum about it. And what is it? Well, in a Z2 orbifold, you have an untwisted sector, and you have a twisted sector. That is the Hilbert space that you construct for the untwisted sector and the twisted sector. And the quantum Z2 is the symmetry that acts on states in the untwisted sector by 1 and states in the twisted sector by -1. And that's a symmetry of the conformal field theory because you can only get the product of two guys in the twisted space giving you something in the untwisted sector. So that's it. That is this guy. The centralizer of this involution was known in the group theory literature, and finite group theorists have their own special confusing notation, but this is the way that they write it. This guy is the group of automorphisms of the Leech lattice, which is a perfectly sensible thing to consider, divided by Z2, because you're doing a Z2 orbifold. And this I'm not really going to explain. It's a finite group called an extra special group. And it has to do with taking the Leech lattice, mod twice the Leech lattice, and constructing a projective representation of that. It's essentially, if you ever have gone through the subtleties of the Frankel-Katz construction of affine E8, for example, there are these annoying co-cycle factors that you have to put into the vertex operators to make the Lie algebra work. Well, this results from those very annoying co-cycle factors.
This is a product.
What?
You got a product.
No. So this is a group that has this as a normal subgroup, and the quotient by that normal subgroup is this. So in terms of conjugacy classes of the monster, this is called I is in the 2B conjugacy class. And then there's another conjugacy class of elements of order 2, which is the 2A class, and it has sigma. And sigma is a symmetry that takes you from the untwisted sector to the twisted sector. And I am not going to construct it. It takes a little while. It uses ideas of triality, but it's not impenetrable to a string theorist. It just takes a little while to go through how it works. And so you see, you can almost understand it if you know that the monster is generated. This you could understand by a careful construction of the vertex operators, and this you can construct with a little effort. It's in a way like it's like a discrete supersymmetry, in the sense that supersymmetry takes you from the Ramon to the Nevers-Schwarz sector, where the fermions are twisted by Z2. This takes you from the untwisted to the twisted sector of this Z2 orbital fold, and it's a very non-trivial fact that there is a Z2 symmetry in this theory that does that. It wouldn't normally be the case. And it is also connected to supersymmetry in that the twist field has dimension 3 halves, so there's actually a superconformal algebra in this theory. All right, so well, I want to tell you 3 amazing things. And then I guess I'm going to be out of time, even though I haven't gotten as far as I wanted to. But all right, so 3 amazing facts. So amazing fact 1 is that these Thomson series are analogs of J of tau for a set of subgroups of SL2R. Maybe I'll call them gamma G, in that the upper half plane mod gamma G has genus 0. That's not true if you just pick some random subgroup of SL2R or a random subgroup of finite index of SL2Z. In general, this can have whatever genus you want. These are very special, and it's quite a mystery why this is true, but it was proven to be true by Borcherds. A second amazing fact. Consider the affine Dinkin diagram for E8. And label each of the nodes by a set of numbers AI, including this guy. So the AI are known as Coxeter labels, and they obey all sorts of wonderful properties. So one way of defining them is that if you take the Cartan matrix for affine E8, then these Coxeter labels are an eigenvector of the affine Cartan matrix with eigenvalue 0. There are 2 ways that Mackay gets into this story. The first of these is something that we have learned about in string theory, which is that there's a correspondence between the A, D, and E affine Dinkin diagrams and finite subgroups of SU2. That shows up all over the place. For example, if you look at C times C mod a finite subgroup of SU2, and you resolve the singularities, you get a set of contributions to the cohomology that have an intersection form given by the Dinkin diagram. You understand massless fields and dual descriptions of string theory by the collapsing of those cycles, et cetera, et cetera. So if you do this correspondence, then E8 hat corresponds to the binary icosahedral group. And the AI are the dimensions of the irreducible representations of the binary icosahedral group. But there's another correspondence, also due to Mackay, which is called the E8 monster correspondence. So Mackay 2. So over here, there was this involution that was a little bit tricky that took you from the untwisted sector to the twisted sector. Suppose I take two such involutions and I look at their product. So these are both elements of the 2A conjugacy class, but in general some distinct elements. And I get some group element by multiplying them. And now I ask myself, what conjugacy classes can I get? Well, there are 194 conjugacy classes, so in general you could imagine you might get any of them. But you don't. The conjugacy classes that you get are 1A, 2A, which is a class of elements of order 2, 3A, class of order elements of order 4, 4A, 5A, 6A, 4B, 2B, and 3C. So the conjugacy classes you can get by taking products of this particular set of involutions are labeled by the affine E8 diagram. It's truly a bizarre and amazing fact. And all right, my last amazing fact is a formula that says, well, let me write it as J of Q. So if C of n are the coefficients in the expansion of the J function, then I take J of some other variable P minus J of Q, that this is P inverse times a product over integers m positive and integers n, 1 minus p to the m, q to the n, raised to the c of m times n, where c are the same, these c's are the same as these c's. And this came out of the work of Borchards, who derived this as a version of the Weil-Katz denominator formula, but for something called a generalized Kac-Moody algebra. And this kind of formula and its generalization to Thompson series is what he used to prove this genus zero function field property. So that is, I guess that's everything that I had hoped to say about Monstrous Moonshine, and I then was going to move on to start the K3M24 story, but I'm 5 minutes over time, so let me ask for questions instead. And
I've got a really stupid question. Suppose I put P equals Q in that formula, how do you get 0 on the right-hand side?
yeah, I guess so.
You get 0 from an infinite product of...
I should have an answer to that stupid question, but let's see, if I put P equal to Q,
Because for every m, you'll have
I guess everything must cancel out. I mean, this implies an infinite number of non-trivial relationships between the coefficients, and those relations must mean that everything cancels out.
because for each m, you'll have n can be minus n,
Oh, okay,
and
good.
then you'll have 1
So
minus
get
1.
some factors.
Oh, okay, all right. So, yeah.
Any questions? Why did you have to get rid of the moduli over here?
Well, I was trying
Could have
to,
been trivial.
I mean, I guess what I was trying to motivate, I was trying to, Well, if you don't do this twist, then you would have a constant term here. It would be 24 or 744 or whatever you want. And there is no representation of the monster that's small. So it would sort of be a sign that the monster is not really going to be a symmetry of the conformal field theory with that partition function.
Well, but couldn't they be trivial? I mean, couldn't the...
You could have 744 copies of the trivial representation. It's true. But, I mean, it's not going to work. But another way of saying why it's not going to work is it was known that the monster had this centralizer of an involution, and that it involved the automorphism group of the Leech lattice mod Z2. So you weren't going to get this group theoretical property to come out right unless you did some quotient. So I think this group theoretical fact is why they thought they should take a quotient, not the argument I gave, which was an argument more toward, from the string theory point of view, we have this special symmetry that can't possibly be there at every point in moduli space, therefore we have to kill the moduli. So that was a made-up argument. I mean, the real motivation for them was this group theoretical fact. But I think it's interesting because I think it is a reasonable argument that if we find exceptional structures in string theory, like things like this, then we're not going to find them at generic points in moduli space. And so to have a theory that has these kind of exotic structures, we will have to fix the moduli. Because I'm not going to find the monster M24 or something else generically in a string theory. So I think it's interesting that it has a connection with fixing moduli, which is why I mentioned that.
One extremely naive and stupid question. Essentially, I mean, now that we have some more insight into it, I mean, with the M24, which you're going to talk about next day, could we say anything about why all these things, I mean, have to be related?
As far as I know, there really isn't a good conceptual explanation. I mean, for example, Borchard's proved this genus zero property, but the proof was kind of computational. It involved using things like this to get very non-trivial identities, and then just doing explicit computations up to enough terms that you could then use general arguments that you would identify these functions, because these guys are determined by a finite number of terms in their Q series. So it was, I mean, it had some deep ideas of using the algebra of vertex operators, but in the end it came down to an explicit computation rather than some conceptual thing that said it had to be true for this general reason. There are some fascinating connections between the genus zero property and computations that Miranda talked about in her talk here a couple weeks ago that are originally due to Duncan and Frankel that involve things that look a lot like computations that you would do in a dual ADS3 description, although I would claim we don't really know what the dual ADS3 description is of this conformal field theory. So it may be, I think we're still looking for it. I think even the monstrous moonshine thing, even though a lot of the original conjectures are proved, is missing something in that we don't really have an understanding of why this amazing structure is there, why there are these connections between sporadic groups and conformal field theory and algebras. I think we're missing something. So hopefully some of the generalizations will point us in a direction of understanding what the general ideas or reasons behind this are.
Are there some very simple examples of where you have non-sporadic finite groups that are very sort of handleable and less monstrous? You can then construct a conformal field theory that's less exotic. You see what I mean? I mean, go to some very simple.
Well, so it's a mixed blessing. You might think, it would be so much nicer to have a smaller group. How nice life would be. But if you think about it a little bit, life becomes extremely miserable in that situation, in this way of doing things, because the smaller the group, the smaller the representations. Yeah. And if I have some expansion with coefficients and I want to know, are they a sum of representations? Well, if I have some small group like S3, and it has 1 and 2 dimensional representations, you don't get a lot of information from decomposing things. Yes. So And actually, so in this generalization that I'll mention next time with John and Miranda, we do have a set of groups, and the smallest of those groups are quite small, the kind of groups that you would love. I mean, that you wouldn't hate because they don't involve. But those are precisely the cases that we have the most difficulty actually nailing down what's going on, because there's so much non-uniqueness in how you decompose some modular form into representations. So the bigger the group, the easier it is to do that if you find some amazing connection.
So I guess what you're saying is Mackay never would have spotted this miraculous thing if the dimensions of the representations were, 2 and 8, because...
Well, Mackay spotted a lot of amazing things, who knows, but it would have been harder, I think.
Lots of numbers, small numbers, it's not,
right.
It's too degenerate.
Right.
Any other questions? Okay, let's thank Jeff.